spacetime lecture. And today we are very happy to have Professor Spenta Wadia from ICTS, and he will tell us about 2+1 dimensional gravity in asymptotic area spaces.
Thanks a lot, Spenta. Thank you. Thanks for the opportunity.
Come on.
So I thought that I dedicated to Professor P.P. Divakaran, who used to be a faculty member here for many years, and he recently passed away. And he was very supportive of the formation of the string theory, mathematical physics subgroup unit, and DTP. Previously, we were all part of the traditional high energy physics, and they were considering us as not doing science, so we thought we'd separate. And I think we did well. But that's why I just want to. And he was a very scholarly person, and after he retired from here, he wrote a lot of articles and an extraordinary book on the history of the mathematics of India. Especially, he brought out the importance and the profound work done by the Kerala school mathematics. So now, this is I have 70 slides. Shiraz?
I never ask questions.
Okay. So,
But Shiraz will stay till 1:45.
Sandeep has Okay, so I'm going to tell you something about how does this work with the point. And there's this. All right, let's okay. So this is a talk about some work we have been doing for the past, I don't know, 2 years, 1 year, with Naveen Prabhakar and Anurag Kaushal. Anurag Kaushal was a student here, and Naveen Prabhakar was also a postdoc here before they get into the ICTS. Okay, so this is about, basically, before I get into all the things, the big picture is how do you sort of describe a very gauge invariant unitary evolution inside the horizon of a black hole? How do you do that? And so this work is basically about that. It was inspired a lot by older work by Kyriakos Papadodimas and Surat Raju, and also by Hong Liu and collaborators. Unfortunately, the name of his collaborator it's a German name which I am not able to say it now. Apologies for it, but it's mentioned here. And of course, many of the very nice papers of Edwin explaining difficult things to common people. Yeah. Okay. So this is the plan. I'll discuss with you the Hamiltonian formalism. Basically, 2+1. 2+1 is because you can do things explicitly, but many of the results will be valid higher dimensions. And then I'll come to the probe scalar field dynamics in the maximally sliced VPC geometry, then summarize. Okay. So there's a lot of words here, but I'll go fast also. In this talk, we address some aspects of Einstein gravity coupled to matter in asymptotically areas. The first part of the talk, we discuss the complete gauge fixing. So the problem of gauge fixing and gauge invariance is central to this subject, actually, and I think it's recently been studied much more than before. Previously, we used to say, just fix a gauge. You can't just fix a gauge. We learned that in gauge theories in the 1970s. Okay, all right. So the first part of the talk discusses complete gauge fixing of pure Einstein gravity. Spacetimes with spatial slices being wormholes connecting to asymptotic ADS regions, and the gauge fixing conditions we employ are maximal slicing. I'll explain all of this. And then we discuss the Hamiltonian dynamics of the reduced phase space after you solve all the constraints and gauge conditions. And we will present the solution of the Schrödinger equation corresponding to the boundary area Hamiltonian and discuss the reduced space-based dynamics, which essentially, with appropriate lapse and shift fields, describes the maximal slicing of the full extended easy black hole jump. All right, this is the limits in which we work. The second part of the talk, which I think is really quite important for the fact that it is also applicable to dimensions greater than 2, really. And so this is about this gauge invariant Hermitian Hamiltonian that we have constructed, that I will discuss. All right. So then there are, we have computed correlation functions, lots of details actually, but ultimately I'll just sketch a few things there. All right. So it's based on some very, what shall I say, a very complicated paper. So we are going to withdraw it and put 2 more papers actually, 1 or 2 weeks now. But the essential points are all made away. All right. So this is the Hamiltonian formulation. Everybody must be knowing about the Hamiltonian formulation of general relativity, right? This is like graduate school stuff, right? Okay. So just very quickly, this is the canonical variables, the metric, and the canonical momentum. This is the Poisson bracket. This is all classical. There is matter. This is the Poisson bracket of the matter fields. And this is the Hamiltonian. Now, how do you obtain this Hamiltonian? Just take the ADM formula for the ds square and just plug it into the Lagrangian of general relativity, work it out, and it'll take this form, essentially. And of course, this is the surface term which you will need because you do lots of partial integration. It's just very much like in non-ideal gauge things. And this is the full Hamiltonian, and this is what you call the Hamiltonian constraint. Okay, and this is the momentum constraints. These are generators of local diffeomorphism in the slice, and this is the operator that takes you from one slice to the next. There's a very nasty piece over here, which is this minus pi squared. This piece is very difficult to deal with in general. But I think the great theorem that was recently proved in the last, it takes a long time to prove these theorems, is that in asymptotically ADS spacetimes, you can always set this to 0. That is the maximal slicing gauge. So you have a nice positive Hamiltonian, lots of things you can prove. And so, for example, if you have asymptotically in DS, for example, you can't do this.
So just to understand,
Yes, sure.
having fixed ADM gauge, that is.
Yeah, that's a slicing risk.
That's a slicing.
Yeah, you have to prove that also, but I'm not going to prove all those things.
Okay, no, sure. Then you can further choose a gauge within ADM.
Yes, because these are first class constraints, as I will sort of mention now. So the lapse and the shifts are the Lagrange multiplier. So that when you vary with n, you have this H plus and HI weakly 0 in the sense of Dirac. So these are the first class constraints. And this is the surface term. And this is defined. All right.
And so you can further fix gauge so that pi, which is trace of pi.
Yeah. So for example, in electrodynamics, you have divergence of E weakly 0.
Okay.
You fix the Coulomb gauge to isolate the 2 degrees of photon of the 2 degrees of polarization of the photon, right?
The extent that this is a choice of time in the bulk.
Yeah.
Notion of time.
Yeah.
Then I don't see why. Do you have a physical way of saying why it's better in ADS and not in?
Because you can prove some theorems. That's the point.
Sure.
I'll show you what you can prove.
But
Yeah.
so is there some intuitive way of understanding?
No, not really. I have to be honest with you. Faraday-Popoff operator, the so-called, does not have 0 modes
Okay, so it's something.
in the small gauge transmissions. That for me is quite physical. So you can't fix that coordinate system. Okay. All right. Okay, so this is the definition of our problem. We work with a small digital constant negative. And, okay. So all this is well known, and as I said, the lapse and shift are Lagrange multipliers. And these are the first class constraints. This is the algebra of the first class constraints of the lapse and shift, which has a very long history. Yeah. Now you have to use Dirac's method of constrained Hamiltonian systems to take this further, and for that we need to fix gauge. So we impose the maximal slicing gauge condition for the Hamiltonian constraint and the spatial harmonic gauge conditions for the momentum constraints. And this second one is very special to 2 dimensions. So in all higher dimensions in asymptotically ADS spacetimes, you can fix the pi equal to 0 gauge. That's absolutely true. However, there are these harmonic gauge conditions introduced by Dirac and others. Those cannot be fixed actually above space dimension 2. But in space dimension 2, as you will see, these things are easily explicit.
Sorry, what is the maximal slicing gauge condition?
Pi equal to 0. Pi is the trace of the canonical momentum, pi ij.
Trace of the extrinsic curvature, right?
So pi is related to the extrinsic curvature. Pi essentially root g times pi minus trace pi g ij is equal to second fundamental form.
The spatial harmonic thing, that's probably not so much of an abstraction. I mean, it's not such a big complication.
You cannot fix that gauge.
No, I understand, but like that's just some choice of coordinates on a slice.
Exactly, but I'll come to that actually if you're interested in this, because this is actually a central problem, how to fix this gauge.
Oh, so that is an important problem.
Certainly, actually, for local compact regions, you can always fix. I can have my own clocks and rulers in some locality here, and you can have yours, but we have a method of comparison on the boundary. So this is very complicated to work with them. It happens in non-abelian gauge series also. You cannot fix the global gauge. It's difficult to define a Hamiltonian. Okay. All right. So there are lots of basic issues here, but let me just go through this, and I'm here for speed, so we can talk.
Sorry, does this completely fix all the redundancies? Trace A equal to some 0?
Yes, it does. The redundancies due to gauge transformations which vanish at infinity, which are trivial at infinity. That it fixes. That's the theorem. All right. So let me go there. So this is
That's
the
partly one way I was also thinking that the asymptotics,
yes,
ADS and DS are different.
very different. Very different. In fact, this generator pi, let me just overshoot a little bit. Pi, that is a trace of pi ij, actually generates conformal transformations of the metric. So what are you really fixing? And this is what I'll show, is that you are fixing the conformal mode of the metric completely by this gauge. You cannot do when you have de Sitter, because in de Sitter, in sense, the conformal mode is very physical.
Yeah, exactly. It's
It
the
gives
whole
rise to the time. I mean, we had this paper on that. All right. So, and asymptotically flat is tough. So, I mean, another time. So it's a difficult one, difficult box. All right. So I just wanted to say this also. This is rather important because I don't see it written in many places, or at least Kyriakos told me that he has never seen this before. So I thought I'll mention it. So there is a Schrödinger equation in quantum gravity. I mean, what I'm saying is, I'm not claiming anything very original here. And the Schrödinger equation is this one, as we know. But then there are these Hamiltonian constraints. So what survives the Schrödinger equation essentially is the boundary Hamiltonian. And anybody who has studied the work of Wadia and Title I in the 1970s knows that something like this has to be. Okay. All right. So our strategy in this talk is mixed. I won't solve this problem as it stands, but we will fix gauge, solve the constraints classically, and obtain the first part of the talk, diffeomorphism invariant reduced phase space. I'll extract out what are the remaining degrees of freedom, assuming a certain topology in the two-dimensional space, and very importantly, the fact that the boundary conditions that we work with are independent of the circle at infinity. So we are working with d equal to 2, right? So we have the topology of cylinder. So it's something like this with circle over here. So we'll assume that the differential equations we solve for the canonical momentum, the solutions are independent of this. Means all the Virasoro generators are set to 0 for this. So just one mode I'm going to talk about.
I mean, you need not have done.
I need not have done that. The problem is difficult and one is looking at it. I've just asked somebody to look at this stuff.
Like a very super space.
Yeah, that's right. So just this particular mode. But this particular mode, the time evolution of this particular mode essentially evolves the Einstein theory from one slice to the other. And if you make a certain, as I'll show, the most of this difficulty here is making all these coordinate transformations. So there is this coordinate transformation from this gauge, which has this degree of freedom, which is time dependent, to the frequency black hole. So if I'm only interested in the physics of the BTC black hole, I only have to worry about its mass at infinity and not about the other charges. But it will be very interesting to really look at the more general problem. But the differential equations are very difficult to solve. Not difficult, but
So far, we're without matter, Spenta.
at the moment, yes. Yeah,
And as you've got these boundary gravitons, and you're focusing on one mode of the boundary graviton.
absolutely.
Now, with the matter, will that be consistent?
Absolutely consistent in the kappa expansion. Kappa square is proportional to G Newton. So if you work it out, these equations to leading order decouple, but at next order,
I see.
leading order.
I see. Once you kappa square is like when it starts seeing the energy of the stuff.
Absolutely.
And then it's back. Nice.
Absolutely.
Yeah.
Good. All right. So let's fix this gauge. So I just want to the good gauge, there is no small diffeomorphism generated by why? Why is there no small diffeomorphism? But just look at the Poisson bracket of the gauge condition with the Hamiltonian constraint. You get this operator. Remember, pi square is 0 over here, so there is no additional minus pi square or anything like that. This operator is positive definite. Forget about this. We can choose it to be less than or equal to 0. Then what I'm saying for matter of that type, this is true. This lambda square is negative. This is important. Lambda square was positive. What I'm saying is not true. So this operator is trivially invertible in the space of L2 functions, all that blah you can do. And so this is the Faraday-Popov operator. It has no zero modes. If the boundary condition is trivial at infinity, that's important. What is V of
Why
phi?
is this operator invertible?
Sorry?
So I just wanted to know why this operator is invertible.
Oh, because it has no zero modes. If you look at the differential equation for the zero modes and put a boundary condition that the zero mode at infinity, that is at the boundary of ADS, is trivial, then you can show that it has no solution. And the way of seeing it is very easy. What you do is you take the operator and act it on some function and take its scalar product with another function. And then every term in that will be positive. And every term is 0 then, etc. If there is no boundary now.
Sorry, just one last question. Why are there no zero eigenvalues?
Well, I just gave you the answer. I'll give you a simple example. Take the Laplace operator, okay? Take the Laplace operator and let's look at the action of the Laplace operator on some function and take its scalar product with the same function. So you look at the integral of psi del square psi. Then you perform an integration by parts. And if you can ignore the boundary term by boundary conditions, then you get grad psi square. that psi square integrated over the volume is 0. That means that psi is a constant, and by the boundary conditions, that constant is 0. Okay?
It is true only when the manifold is compact.
No, my manifold is not compact here.
Okay, sorry, I wanted to say it the
That's
other
why
way
I put
around.
boundary conditions.
Yeah, okay.
Okay,
Thank you.
yeah.
Sorry for the disturbance. I won't say much after this.
No, that's all right. But everybody here get hungry. That is my problem. Yeah.
So sorry,
that's okay.
Spenta, but
No.
if you took a scalar, I assume.
If you are willing to bear with me, I'm willing to talk to you for hours. No problems. Tell me,
All right, keep it.
please.
But if you take a scalar field,
Yeah.
I think the conventions are that if you have a scalar field with the right side up potential, that would be V greater than 0, right?
Yeah. So you don't look.
That would be the natural kind of potential.
No. So this D square is the negative definite operator.
Right.
This is negative definite
Right.
operator.
Lambda is negative.
Negative.
But can't V be positive for a right side up potential? I mean,
No, because in general, suppose I have a m square phi square term, it can spoil this problem because it has a positive and negative, so it can
that's what I was
spoil.
thinking, yeah.
So I don't want to consider that. So if I have a standard scalar field like with a certain mass corresponding to some operator in the boundary theory, then that I will treat perturbative. So then this is true to leading order. That was the just true to leading order. Just forget about this. No additional thing. I mean,
And massive scalars with below the
this is this Friedman.
below the marginality.
Exactly.
That will
If you do that, this will be okay.
This will be okay, but I mean, the irrelevant ones, you have to be more careful.
Absolutely.
Because
Absolutely. Yeah. All right. Fine. So, okay. Let me go ahead. So, the same differential operator has 0 modes of physical relevance. And this is important that now basic point is that we just see that differential equation essentially is also satisfied by, for example, the lapse function. But I know that the lapse function is important in the boundary theory because it corresponds to time translations in the boundary theory, right? So now I have to look for solutions of the equations of this solution of the lapse function consistent with the gauge condition and what is allowed at infinity. Okay, so that we are restricting to certain types of lapse functions, which do not depend upon the boundary circle. But I'll come to all that a bit later. It's just to sensitize you to the fact that there are solutions of this equation which are important physically. It's like in gauge theories. I mean, if you want to talk about electric charges there in the system, you don't talk about asymptotic rotations, then the gauge transformation cannot go to 0 at infinity. It's just that. Just basically all that. Okay, something. Okay. So I made this important point here that the boundary conditions for the lapse and shift differential equations allow for these type of angular dependence. There are modes, and these modes generate the boundary Virasoro, right? And you see all that. But we will not discuss this mode generating problem today. So the question is, which I almost answered, what part of Gij is fixed? Like, for example, in gauge theories, if you fix the Coulomb gauge, you are putting the longitudinal part of the photon to 0, right? So what is the analog of that over here? That's what I'm doing. Okay. So, so pi generates the Weyl transmission. So to isolate the conformal mode, this I do the standard separation of variables, right? The metric as g twiddle pi twiddle times the exponential of 2 lambda, which is the conformal mode, and assume that the conformal mode on the boundary goes to 0 because both Gij and G twiddle ij, this is the boundary condition, both have R equal to 2 lambda. This is the Einstein condition. asymptotically. All right. So you do that. So you separate out this one. All right. And then you plug it in to the Hamiltonian constraint equation, this stuff. And you get a very complicated equation, which is called the Lickner-Lewis equation. You know, the decades people have spent on studying these equations, especially in high dimensions. And now there is some other thing actually you can do, and this is a theorem due to Yamabe, which says that you can write any metric actually can be written as a conformal mode times this G twiddle, where R twiddle is equal to nu lambda everywhere. So there is a metric. I extracted the conformal mode, but I can further use this theorem that if the metric asymptotically is ADS, it's all classical physics. I mean, nothing quantum here. Then everywhere I can choose. So these things are not obvious, at least to me, and people have proved them, and we are just using it to.
So R is also 2 lambda. R
Yes.
created out of G.
Yeah.
So roughly this is like del square lambda is equal to
Yes. Roughly true. Right?
Yeah.
That's
because by equations of motion R is 2 lambda. You're setting R tilde up to 2 lambda. So the extra part in R coming from the conformal has to be set to 0.
absolutely right.
Yeah.
That's Yamabe's theorem. Somebody.
Lickner-Lewis equation is describing a space-time which is not necessarily follows the Einstein equations.
The Lickner-Lewis equation is the Hamiltonian constraint. So
Yeah,
it is
but
part
Einstein
of the
equation.
Einstein-
Okay. What was why was there a pi is equal to 0 maximal slicing gauge condition? Where did it come from?
Oh, where did it come from? I have to choose some condition to remove the additional degrees of freedom in the gravitational field. Right?
Is there some justification?
The justification is, let's say, for example, let me give you a gauge theory example. I mean, you have a constraint, right? Gauss law constraint is there, right? So you fix a gauge corresponding to that, which is the Coulomb gauge. So the question, physically, why you do it is because A mu, the gauge field, has more degrees of freedom than just the 2 degrees of freedom which the physical photon has. And that's the reason. It's very elementary, actually, even though mathematically
The
all this.
analog is for metric degrees of freedom here, not for the gauge fields.
I just gave you an example from gauge theories, which also
Yeah,
applies.
but, we are considering metric here, so
Yes.
it's a rank 2 tensor, and that was a vector field.
Oh, no. That was just an example I gave for why we have to fix gauge to remove redundant degrees of freedom. Okay. All right.
So this
yeah.
topology of this slice is what is?
That's very important. Yeah, I'll come to it. Sure.
Can you think of Hamiltonian constraint as secondary constraint? Is it
So yes, of course. I mean,
Is
the
it like-
Hamiltonian, point is the Hamiltonian constraint and the gauge conditions, they form a set of second-class constraints. Certainly, that's the point.
Okay, so after imposing this maximal slicing condition,
Yes.
whatever follows from the Hamiltonian constraint will be your secondary constraint.
I have to compute the Poisson brackets. I have to then look at the Dirac bracket. There's a standard procedure of doing it. And when you do the Dirac brackets, then all these conditions can be strictly set to 0 in all of phase space. It requires a little bit of studying it. May not be totally obvious.
So it's R tilde equals to lambda, is that special to equals to?
No.
It's more general.
No, they're all very general. Yeah, no, many of these theorems are completely general. Only for
I thought
asymptotic.
that you're allowed any G tilde.
This is
Space space is just general G tilde.
Yeah, so it seems to me that what's happening here is that it's a conformal mode, which is determined by the Lickner-Lewis equation, and it's this type of simple negative curvature metric everywhere. Then, of course, the difficult part is what is the topology of the 2-dimensional space. So then there are very complicated solutions. But I am going to work with a very simple topology of a cylinder with only one modulus, the throat, but you can have a handle, you can have 10 handles. That's a very difficult problem. I wouldn't know how to write.
So I should think of this as some sort of uniformization theorem in kind of which. See how we can
Explain what is uniformization. Oh, I know uniform.
in two dimensions, in two dimensions, exactly. In two dimensions, we take out the Y factor
Right.
and the metric can be put in
Yes.
some canonical form.
Right.
And here also it looks like
Yes, looks like that. Yes. This is many of these things, the Yamaway theorem, the Lichner's equation, solutions, uniqueness, all of this is valid for t greater than 2 volts.
What was your question on that?
I was surprised that you could, like, it feels like essentially, I was thinking that in phase space, G should be just arbitrary, G and phi are just arbitrary, up to this Hamiltonian constraint. But it seems like R tilde equals 2 lambda is very restricted. It's like,
But you've also got a conformal factor.
yeah,
So suppose I take R tilde, I take R.
Yeah.
Oh, it differs from the R of R tilde by this conformal.
conformal factor. So,
But you're just splitting the metric into a conformal piece and the rest, and you're using that to set up.
I would have,
That you feel is unintuitive.
uncomfortable, but okay. In 2 dimensions, I certainly believe that. Anyway, I don't want to go. We can discuss.
Just one confusion about the decomposition. Are we requiring G tilde to be unit determinant?
No. No. I didn't do that.
Sorry, but if you don't mind, just one second. So, suppose we have R as something.
Yes,
Now we do this conformal transform.
yes,
So R becomes R tilde
yes.
plus some like del square phi.
Correct.
Now can't we then invert that for del square phi?
That's certainly fine, but I was thinking about
Del square now.
solving the Hamilton constraint, right? The Hamilton constraint would solve, so you have some G, which is written as e to the 2 lambda by G to the 1. And then I was thinking that the Hamilton constraint would allow me to solve for lambda in terms of everything else.
But this point 2, is it true off shell or on shell, Spenta?
Which one?
The second bullet. We can always write. I thought that was just an off shell statement.
Option.
Off shell. Yeah, it's just a statement of decomposing a metric. Forget about any constraint.
Okay.
Then it's clear, right?
Oh, then,
So there are 2 wild factors here.
okay.
So the first wild factor comes from the conformal transformation that we fix. But then that class of matrix also can be written as another wild factor times a metric which is R twiddle equal to 2 lambda everywhere. Not only asymptotically.
So that is a statement about metrics has nothing to do with.
I see. Okay. Then I misunderstood.
Yes.
How do we distinguish the classification between topology and the differential geometry part, the metric? Meaning both are distinct configurations and we cannot fix a single unique topology like that of a cylinder for this scenario, I believe, because we are doing a quantization.
Why don't you wait a little bit?
Shreyansh, please limit your questions if you don't mind.
Just wait a little bit and I will come back to you. Okay? Okay. All right. So, all right. So this is, let me go ahead actually. So now let's look at the generators of the spatial, the momentum constraints that generate local diffeomorphisms in the 2-dimensional slice. Now we restrict to 2 dimensions because from here you cannot really make general statements. All right. So I'm now going to discuss all this harmonic gauge business. Witten wrote me a letter that this cannot be done in general, and I mean, there is a really serious issue of how to fix a global gauge in general relativity. It's not easy, but you can always fix it locally. We know that in gauge theory also, but you cannot do calculations very easily that way. You cannot do a So the maximal slicing gauge was very good because it enables me to discuss a slice to slice Hamiltonian flow. It's just like the A0 equal to 0 gauge in gauge theories. If you cannot fix that gauge, it's difficult to do a Hamiltonian formulation.
And Witten's comment is that in other more popular topologies.
Not, no topology, just this simple topology. In higher dimensions, you cannot do this, yeah. He didn't say higher dimensions, but we knew that with d equal to 2, we could do it. Yeah. So shall I proceed? So these are very interesting questions, and we have struggled a lot actually trying to understand these things, but all right, so so this is the gauge you fix. This is a fixed gauge which was discovered by Dirac. So the 1 upon d actually in d dimensions. This is now 1950s. In 51, Dirac paper is 51 paper. Amazing. Anyway, so this is the gauge we will fix, and we could work it out. We can show that this is good gauge in 2 dimensions. I will not discuss all that too much, but you can all do it as little exercises, the students, if you like to. I don't like to give problems to my colleagues.
Some of us couldn't solve them.
But anyway, so this Poisson bracket actually defines a what I call a Fourier-Popoff type of operator, which actually is invertible over here. And we specialize, actually, this is the point, that our slices are cylindrical. They are like topology of a cylinder, like a wormhole, basically. All right. So now let me go ahead. I'm just on slide 15. All right. So once again, you can work all of this thing out. And again, so you see, I mean, some of us work out differential equations, but one of our collaborators knows a lot of good mathematics actually. So we arrive at the same result. And so let me sound very erudite and say that any 2-dimensional surface with constant negative curvature can be obtained as the quotient of the hyperbolic plane by an appropriate fixing group. This is a consequence of what is called the Tilling-Hoff theorem in differential geometry. So what you do is you take the upper half plane, I mean, I understand all that, and quotient it by essentially the diagonal matrix e to the, let's say, m and e to the minus m, so that it's determinant 1, and you quotient it by that, n should not be 0. So you essentially form a cylinder, right, with sides identified, and that's what it is. So, but if you are not mathematically inclined, you can actually solve this differential equation, and you can show the same result will come out.
This is a statement of given the cylindrical topology.
Yes. This one, particular one.
So in general, it's true.
Huh?
It's true in general.
In general, it's true, but specialized to here, yeah. So the subgroup of the Fuchsian group that I'm talking about is just a diagonal matrix e to the n, e to the minus. And yes, sure.
Just to get your gauge fixing in your head, this is the order I'm thinking. I first do this e to the power lambda times r tilde. Then I impose your pi equals 0 for gauge that effectively fixes lambda in terms of everything else. And then I do the harmonic stuff, which gives me coordinates on each slice.
Yes, absolutely correct. Absolutely correct. Yeah, that's the whole show actually.
Yeah.
And the fact that you can actually do it is the real work. That's an acquisition they've done. Okay, fine. So okay, all said and done, this is the answer of the 2-dimensional metric with this topology is just given by 1 modulus, and this theta goes from minus pi to plus pi. So this is our, and it's an open space, so the costs will diverge there as expected. This is a conformal factor of ADS, and so it's one parameter. Sorry, excuse me. One parameter family of metrics, and this is the modulus. Okay.
So you're not considering the rotation.
Sorry.
This is not the rotation. This is like the ordinary BTC.
Yeah, see, up till now, I have not told you what is a black hole or anything. I'm just solving the Hamilton equations of motion. Einstein equations I'm solving. Sure. And that's the interesting thing, that if you solve it in certain coordinates, you won't recognize it's a black. I'll come to that. Yeah. So this is the result of fixing the spatial harmonic gate. Okay. And this is the degree of freedom left over. So you see, the degree of freedom corresponding to the conformal mode, which you were talking about, is fixed by the Lichtenowitz equation because somebody proved that there is a uniqueness theorem. And that actually, that solution depends only on theta, the spatial. And it does not depend upon, I don't have to assume that. The uniqueness theorem tells me that the conformal mode actually is uniform on the circle. Yeah.
Here, this geometry, Lorentzian geometry.
This geometry is
Euclidean. But I'm saying if you look at Lorentzian geometry, you can think of it as just ADS3 and quotienting it by something to get this group that you talked about. You can extend its action on the entire ADS3. And I'm just trying to ask Omkar's question in a different way. But now, if you did quotienting by a group that is kind of somewhat rotated within the conformal, within the isometric of ADS3, then you will get rotating cases, right? And then will depend on that. So here you that can also
yes. So this M is a function of time because I am at fixed time slice. Time is implicit Hamiltonian. Okay. All right. So where am I? Plugging in the expression Gij. I mean, it's very solved all this. This is all for pure gravity and.
I
have solved the
space has only one real degree of freedom which can't be seen.
Exactly. And the moment, because you see, I have not solved for the momentum constraint.
No.
This is where the assumption will come that the second fundamental form actually is independent of the circle. That's my assumption. And then these are canonical conjugates. So I'll come to that. Yeah. So now I want to work entirely in terms of the second fundamental form rather than by ij related this way. And I have now solved the momentum constraint equations. So again, I have to solve differential equations. So I need to have boundary conditions. And these are equations which can be solved formally very easily because they're linear equations. But I am only going to restrict myself to the zero mode. Because if I look at this small system, then it is this small system that corresponds after the gauge transformation to a static ETC black hole with zero angular momentum and mass. I mean, just the simplest thing to do. Okay, so this is a crucial assumption. The fact that the A2 phi actually is independent of phi. And this will correspond to the maximally slight ETC black hole solution after a coordinate transformation. And the solution is this, the momentum constraints. The higher the charges will appear. And phi dependent solutions for K we will not consider, which I'm not considering. All right. So this is the phase space that corresponds to.
Just out of curiosity,
Sure.
People worked this out in the general case, like the high dependence, showing that the full base.
We are trying to. I asked Samrat to look at this question.
Isn't this what the asymptotic symmetry people do? So it should be marrying that with some.
I mean, Brown and Heno have investigated this problem, and they have this boundary Virasoro. They have identified the central charge of that Virasoro with accompanying us. So all that work is there, certainly. Yeah, but we are approaching it from a very different point of view, for different reasons. Yeah.
And T was just boundary time. Capital T here.
Wait.
No, what is it? Yeah, sorry.
See, there is a slice
Yeah.
labeled by T, and this is the whole point. That the maximal slice agrees with the time of the left and the right boundary up to two constants, which we set equal to 1 in our case. Now, if the constants are not set equal to 1, you are looking at this problem Kuharsh was Kuharsh, Kuchar. This problem people were discussing in Chennai. I was on the Zoom that time. So Kuharsh basically considered that freedom, the difference of the left and right boundary line physically, and the mass become the conjugate variables. And he was able to write down the Einstein action in terms of those variables. And what we could show is that, our degree of freedom can be classically transformed to what Kuharsh. It's like going to action angle variables. Because for him, the one collective coordinate was mass, and the other was the difference of time. And all of this business of the asymptotic mass and the time difference and all that, and then the family of black holes you have to consider for this well-defined algebraic quantum field theory in the paper by Pennington, Witten, and Chandrasekharan. So it's all connected. This is the mode they are talking about. This cross product business is exactly this. So I didn't realize that, but in that meeting, people raised this question that you are missing out a degree of freedom. So no, we could show that by a canonical transformation, our modulus and our phase space maps into what Kuharsh did, but Kuharsh's phase space cannot be quantized. This is a very trivial reason why you cannot make classical canonical transformations in quantum mechanics, as you know.
What is the physical interpretation of RM?
I don't know.
It's like the area.
No, see, it's n squared d phi squared in some sense, so it's related to the throat actually.
It's the area of the black hole, the area of the horizon.
No,
It's not.
oh, no.
It's like the minimal area, isn't it like that? Is it like that?
That's the area.
We will see. Let's see a few formulas. I couldn't come to a conclusion. For example, where does this modulus belong in the conformal field theory? Because it is not actually belonging to the left conformal field theory or the right conformal. It's not dependent on which boundary. So it's something which I have not figured out.
But it's not Omkar is saying the area of the horizon, it's not in the minimal area as you go along the cylinder at theta equal to 0. You're working.
Theta equal to 0. Okay, so the point is that the value of the metric in order to compute this area and stuff like that, the metric also has the Lichtenowitz factor,
Lambda.
which has this thing in a very difficult way.
Yeah.
So it cannot.
I see. So that's the tricky part.
Yeah. So. Yeah. Okay.
So you would have to solve that Lichtenowitz, obtain lambda as a function of n.
Yeah, it's you see the Lichtenowitz equation solution here turns out to be one of the Jacobi elliptic functions. Very complicated problems, but so you cannot draw this simple conclusion. That's all.
Okay, thank you.
Shall I go? Go on. Okay, so now this is a technical thing. So these equations can be solved in our dimension exactly. Okay, with the assumption of that spherical symmetry. Not this one. This one is unique, exact. I'll tell you why the Lichtenowitz equation solution does not depend on why. Because of the uniqueness here. I found a solution and it's unique, and therefore it's quite remarkable. But you cannot say that about the equations for the momentum constraints. So let me go on now. You can do all of that, and this is the solution. And this variable c, which appears in the solution, is solved by this implicit equation. Okay, this is the complete elliptic integral. Everybody must be knowing all this. Elliptic functions, elliptic integrals.
Please. That's the kind of thing you try to avoid.
I had Jasmine Isaac on my bedside when I was a postdoc. That helped me actually find the third order transition. Because the solutions were in terms of elliptic functions. But anyway, you would have figured it differently. Okay, so this is what it is. This is the solution of the liquid. And this C is determined this way. And then basic picture is this, that this is how the solution of the Nervous equation looks. It's even in theta. And this is how the function, as a function of C, K star, this object K star function of C is important because, as you will see, the Hamiltonian contains K star plus K star inverse within this. Okay, so once you solve all this and then you solve the lapse and shift, I won't go into all that detail. You can do all this, go on and on and on. This C and C twiddle is important because this is the asymptotic value, because if theta is equal to pi upon 2 or minus pi upon 2, this term is not there, right? So this is the lapse with this factor in front, which diverges usually, and times this constant C and C twiddle. So this we are setting equal to 1 in our way of doing it. You can actually retain it throughout and it doesn't do anything. So this was the degree of freedom the people were saying we were missing, but our degree of freedom is already there in the modulus. Okay, all that is very, very technical, but it takes care of a lot of questions a lot of people had in that meeting. You were there. Okay.
Before you go ahead, could I ask a technical question? So because you have Jacobi elliptics, and as you know, all the Jacobi elliptics are just some combination of Jacobi theta. Do you know why there is some? Do you know why there are these modular things coming up? Do you know some CFT answers for?
I don't know, but this might be part of the Loga paradigm, right? You never talk on the Loga paradigm. I don't know the answer here. Okay. Shall I continue? Okay. So, all right. So these are the solutions for the lapse and shift. All of them can be just found. These are simple things. There's nothing great about. Finally, once you know all the solutions, you know what is pi and you know what is G, right? G dot. So you plug it all in and work it out, and this is the answer. It's capital T, which was the asymptotic value of A phi one, and times m dot upon n squared. Classically, n is not 0, so this is now see we looked at this problem for a very long time. Actually, I mean, you know, this is a mechanics problem. How do you sort of do the classical mechanics of such things? You solve the classical equation of motion, which we could do. But if you want to quantize it, then how do you do the path integral and this and that? So it turns out that this problem is related to the coadjoint orbit of SL2R, certain coadjoint orbit of SL2R. I'm not going to get into all that in the upper half plane. But I am going to solve it in the physics way, which will like, I'll solve Schrodinger equation rather than do any part.
Just since you mentioned it, I'm also beginning to study this, but the coadjoint orbit, which normally gives us, for example, when Shatashvili and so on quantize the coadjoint orbits, this is a different coadjoint.
Yeah, this is just mechanics problem.
No, but since you're relating it to some.
Yeah, you know,
So
no. I know Alexei is very well. I mean, the point is, this is Marxism. It's just about 1 degree of freedom.
But it is related to a
This I mean, you see,
okay. Anyway, so
what works out is this form that is written there. See, if you write dt wedge dm upon m squared, this is the symplectic form in the upper half plane. That's all I'm saying. Or kuch nahi bol raha. Okay. And learn to quantize that.
In the reduced phase space.
Yes, that's all.
Okay.
Yeah. Spenta, can I understand it like the previous comment that you made about ocean T?
Yes.
Right. So there is a group of subgroup Anseldua, which is used to quotient the full geometry, these three geometry,
Yeah.
to obtain this geometry. So
Yeah.
in that sense, the solution space should be the action, how you embed the group, which is
Yes.
related to its adjoint action of the group on that subgroup. And then that is the phase space that you're saying.
That's
So this suggests that even the bigger phase space, which is this even including the rotations, should be
Eventually, it should work out.
adjoint
Yeah, I expect this actually.
Okay.
To be related to coadjoint orbit of your solver and stuff like that. But my interest here is a little different, so you have to let me get there. I want to go through the horizon safely.
So in the end, your action has two quantum mechanical degrees of freedom,
Yes.
M and T,
Right.
and that's the action.
Yeah, that's the action. And now what do you do?
Can you remind us what were M and T in your
M is the modulus m square d phi square.
M square d phi square where?
So the
At the bottom.
two-dimensional
Okay.
two-dimensional manifold is parameterized by theta. It goes from minus pi upon 2 to plus pi upon 2.
Okay.
And by 5, it goes from 0 to 2 pi.
Yeah.
Now you write ds square equal to 1 upon cos square theta, that's the answer, times d theta square plus m square d phi square.
Right.
That's where it comes from.
Okay.
Just that.
And T, what was T?
T was the asymptotic value of the canonical momentum. It's related to k theta theta and k phi phi.
Nice. Thank you.
Yeah, k theta theta I think is minus t and k phi phi is minus t or plus t upon m square.
Thank you.
Yeah, that's what it is.
Just maybe you'll get to this, but all this multi space, all of this is going to contain empty areas, black hole areas, all of that. You'll get to this.
Yeah, okay, wait.
Is the question about the range of your coordinates?
Which one?
So the range S for M and T.
So classically m is either m is not zero.
M is positive.
Classically. And this t goes from asymptotically plus.
M is positive, correct?
Yeah,
It's
classically.
M greater than
Yeah,
zero.
because you're not happening. So I don't want to get into all this coadjoint orbit stuff. I want to say that my choice, so this is a choice of canonical variables is this. Okay, and then I saw.
Sorry, Spenta. Now don't beat me. Last
I'm
question.
beat you, man.
If it were me and I saw a symplectic form dt wedge dm over m square, I would say go to the variable 1 over m and then it's dt. But you have done it, so you've obviously done it more correctly.
The problem is Hamiltonian is extremely complicated. Look, the Hamiltonian depends upon the solution of the integral. How are you going to solve this type of problem? So there's a trick.
The issue might be that 1 over m is singular m equals 0.
But he's excluding m equals 0.
Yes.
That's why I
Excluding classically, but I see quantum mechanically, the wave function don't care.
Okay, I see. This Hamilton, why do I have to worry about the Hamilton? Now you reduced it and gave me this mechanical system. I'll just work with it and quantize. What is this Hamiltonian now? Sorry, I'm missing something in the whole setup.
Yeah.
P q dot minus h hota hai na.
How about the first order action? That was the Hamiltonian, no?
That is just the
Boundary.
pi g dot.
Oh, so the
I just calculated the pi g dot.
okay. So it's
And
much
minus-
more, it's a much more
Minus the
complicated-
boundary Hamiltonian is there, no?
Okay. Much more complicated.
Yeah.
Okay. Then I understand. Sorry.
Wait for you. Keep your hands off. Remind me of the Feynman thing, Feynman's solution.
And what was the range of T, capital T? Minus
Minus
infinity.
plus. Okay, but this is what classical physics gives you, but quantum mechanically, if I am making a choice here now, as I said, of what the canonical variables are, they are these. Look, this is the Hamiltonian assembly. Depends upon Q in this very complicated way through the solution of the elliptic integral. And you can do numerics actually, nice numerics, and this is what it looks like as a function of Q. Very nice. Very nice formula this is actually.
And what was Q once more? Sorry, it was TM squared.
T upon n square.
T upon.
Thank you.
If I were to compactify T for just a minute, then I would get a finite dimensional phase space. Because now it would be like a magnetic field on a torus.
Why are you stating my problem?
Just to get orientation. Sorry, I don't
No,
remember.
no, no, no. I mean, it's fine, but
M is not compact. Sorry, no, I was thinking
N is not
No,
compact,
you're right.
no.
I would.
Okay. Yeah, no need to put just.
But will be in the range space?
I'll tell you what, so our phase space consists of pi and g. So these are functions on the two manifold. Functions of two manifold at a particular time. There are infinite degrees of freedom. But when I solved the constraints and the gauge conditions and removed all of them, and in this very simple problem, I could do that. Because in a sense, frankly, there is no real good gravity in 2+1. There is not even Newton's law in 2+1 dimensions. The real story begins in one higher dimension. But these are some toy problems we try to do.
And what is K star?
Sorry?
What is K star? In this
So K star is the modulus of the. I'll show you. This see, this is the elliptic, complete elliptic integral of first kind. It's implicit. Actually, that equation comes from looking at the boundary conditions over here. And if you look at the boundary condition problem in these coordinates, it's a little difficult, but there's one more step you should take. See, the elliptic integrals or elliptic functions have various different representations. One is in terms of trigonometric things like d theta 0 to pi, something. The others is in terms of just ordinary integrals over square root of some product of rational functions. So you take that formula and then you will arrive at this.
So you solve that transcendental equation for K star and then that gives you the Hamiltonian as 1 by K star.
Exactly. Yeah, that's right. K star is a function of C. Okay, so let me move because by itself it's a all very interesting problem, but I want to get. Okay.
Sorry, does your Hamiltonian suppress m equals 0? Is that very high energy? Near m equals 0?
No,
No.
just see what happens. This is the point, actually, what I want to make about. We have a classical theory and a quantum theory. All right, so this is the classical problem, and the ADM mass is just given by this formula in terms of these two. This is all classical up to now. And later we will see that n is the value of the ADM mass of the BPD black hole. And the time-dependent equations are difficult to solve, but you can do the phase portrait actually at fixed values of energy, and this is what it is.
Oh, sorry, Spenta. Did you show us a formula for H as a function of m itself?
Sure.
Where does m and t in that?
Sorry.
I thought your variables are m and t.
Yeah. So.
He went to Q and
He went to Q. Q and P. I see.
So redefine what is canonical variables. This is, I mean, what to do really? I did it so that I can solve this problem, and this was my choice. After all, this is there's an operator ordering problem. All types of issues are here.
Yeah.
In this type of problem, so I chose the Laplacian as my Hamiltonian. You see, I mean,
How can I see the Hamiltonian once again in Q and P?
sure.
Does it go to infinity if Q goes to P? No. H, and this H is a high C, but it looks like infinity as Q goes to, right? Because Q squared. Yeah, fine. So then m equals 0 has very high energy. Okay, good. Let's repel away from it.
It will repel away.
Yeah.
Yes, and we'll see that the exact solution tells you that.
And that's good because we had an infinite phase space volume near m equals 0.
Yeah.
So we should be repelled.
Okay.
Yes.
Good. Okay, so these are the phase portraits. I mean, this you can work out. It's not very difficult. I'll give you some idea of the classical phase space, and it's all very well did, perfectly ordered. And now you want to quantize it actually. So you want to quantize this. So our description for the quantization is to use this operation. the Laplacian of it. This is, you have p squared times some function of q to quantize. You got to make a choice. You can do p squared h plus h p squared, all that. But we choose a Laplacian. And then the problem is very simple and it is exactly soluble. This is just some free particle in different variables. You can change variables. You can change variables. This is 1 upon h actually. And because this is very well defined, this map is very well defined. That's very important actually. And the domain of capital Q is the same as the domain of Q bar. So you map one problem into another. And now it's a free particle problem. You can just work it all out. Everything is simple. You can do everything. So the eigenfunctions represent quantum states labeled by a real number p with energy p squared. As we will discuss soon, the classical solutions in the reduced phase space correspond to the two-sided BTC black hole solution. Hence, we may identify the energy eigenvalue with twice the mass of the black hole because it's two-sided. So you have this continuum. It's all very disappointing result. You shouldn't get a continuum. Because we are working at n equal to infinity or G Newton going to 0. This is the problem. Okay, so this is the explicit answer. These are very nicely delta function normalized solutions, and so you can do this. And then you can match it with the classical solutions also. Just this action. So this is just Hamilton-Jacobi theory. And if you know the action at fixed energy, you can actually do the variational calculation to get the Newton equations by a redefinition of time and stuff like that. So I mean, all that can be done. So we see that this is a soluble problem, very quite disappointingly trivial, I must say. I mean, and it has a density of states of free particles. This is 1 degree of freedom. This, I mean, it's difficult to get at, but once you get that, it turns out to be nice. What was the density of states? Free particle density of states, yeah. Yes. Oh, it doesn't have the density of like the SYK model or something. I think those boundary gravitons. But you see, this is, I'm not considering all boundary gravitons here. We're just talking about one mode.
Of course.
And it will be very interesting to pull out a black hole density of states from this formulas. Yeah.
So what you might have expected is that this is the spectrum of primaries, and then that the other stuff just makes it all the descendants, right?
I agree with that.
Yeah.
I agree with that. I completely agree with that.
Yeah.
But for that, I have to include the Virasoro.
Yeah. But we sort of know what the answer is. So,
Absolutely right. Right.
Yeah.
But I could not actually really solve those problems for the fundamental form, for the momentum constraints, when phi is a function of k is a function of phi. And it becomes very difficult. Maybe one should use some existence theorems for some boundary conditions. You know, let's use some mathematics things, and maybe it's possible. I think that's a good route to take. Those equations are almost impossible to solve. At least.
Spenta, you haven't really said G Newton to infinity, have you? I mean, isn't your quantity, this is what is bothering me. Because in G Newton going to zero limit, you would expect infinite central charge and you would expect some kind of continuum, right?
Point. I didn't do anything yet.
Do that. So
I didn't do that actually. I didn't do that. Yes, you're right. So yeah, of course, these are the things that are bothering me.
what's the answer to that in JT gravity?
In JT gravity, great question. In JT gravity, you get I don't know. Let me give the dissenters.
Sit out there.
Okay, let me give I think the ADS story is that you get an infinite number of states, but the matrix theory is in the double scale limit with also infinite rank. You know, and you map the eigenstates to eigenstates very precisely.
Here, one
So-
state you
so,
are able
you
to
know,
map. You are.
Because of the double scaling,
No, I understand. I
But
mean, here, no, I think
Maybe
in
I'm
the
wrong.
limited sense, this is correct, actually. There's nothing wrong
Yeah,
here. That for every, so there's a band of energies you can consider. For every value of the spectrum, there is a massive black hole in the bulk. And this accords with what all these other people are saying in these algebraic quantity theory papers.
Because you have a L2, whatever degree
Exactly.
of freedom, you
Exactly.
have also seen
Exactly.
that.
Exactly.
But Sandeep, suppose we had we had two quantum systems of finite central charge. Each of them has some discrete spectrum in a rough band, so you should expect the double thing to be discrete, right? I mean, with finite everything.
I mean,
Discrete meaning not have a
You're
continuous.
saying 2D, is your comment in
Yeah,
JT? But I think JT is not a CFT. JT is this double scale matrix theory.
But suppose we were doing SYK, two SYKs at finite end. Then everything would be nice. And
Absolutely.
no continuous, right?
But how do you compute?
At finite
Very
end,
difficult to
finite
compute.
end.
Yeah.
But that's not the precise map is not JT
going
to SYK. The
Absolutely.
precise map is JT to the SSS matrix.
Also, you're doing canonical quantization about the leading sample, right?
That's what I was thinking, that they would get exponential corrections, which will make it finite.
Exactly.
That's how somehow I thought how it would work.
The non-perturbative.
Yeah, the non-perturbable. But that's not, I think, what Sandeep is.
At least the number of states, in that case, is it true that the rank gets cut down?
The discrete, the exponential scale.
Yeah.
Because e to the power s.
E to the power s, exactly. I mean, minus s.
But the number of states is still continuous.
So Sandeep's point is that this double scale matrix model is strictly in the end goes to infinity. So you were saying, therefore, there's no.
Actually, let me just say, nobody has proven that at large and finite, as opposed to the double scale limit, you have a gravity theory. Namely, you can correct JT, in a systematic way. There's no proof of this.
But it may not be also true.
And it may not be true. I'm just saying. So, in terms of what we know, but here I don't know. I thought, as you say, if you're working at finite C, wouldn't you have expected?
Yeah, but even here it might be exponential corrections, right? A new saddle. That's one question.
So, but Spenta is quantized exactly. Where is
There's no, for instance, topology is fixed.
Yeah, that's right. If the topology is you have to sum over, then of course you will.
that you can't do in the canonical framework.
Shiraz,
But I mean, isn't the point that there is a consistent quantization of gravity in the canonical framework at fixed topology?
Yes.
Does it or does it not give the black hole entropy, right? And isn't Spenta saying that it doesn't? I mean, modulo all your caveats.
So this
I'm
was
asking.
exactly the problem that's bothering me, because that's why I made this. I deleted some sentences here because I knew that there will be a discussion. But anyway, there's a discussion.
Okay.
So the point is that can we have the fans?
Yeah.
Sorry. What I'm trying to say is that if you do this, it's just a free particle. The density of states for the black hole is both the exponential of root m, as we know. But m is the mass, basically. So that, I'll tell you what my understanding of that is. Okay. So we have these maximal slices. Okay. So there is a solution, and I'll show you that you can map diffeomorphically this set of coordinates which are propelled by m and t in the slices into the BDZ black hole solution. Okay. So the question arises, where did the entropy go? Where did all this stuff go? So my understanding is the following, that if I look at these solution in the maximal slice, which I haven't shown you because it's quite complicated, but we'll get to it. It has an area. There's a horizon, there's an area. And I associate that with the entropy. But this fellow, this 1 degree of freedom is just telling me in this gauge how to go from one slice to the next. If I took into account all the boundary gravitons into account, then I may be able to make the type of statement that we are looking for. There will be a conformal field theory, I know how to compute density of states.
Then you have the cut down.
So could I make a suggestion, just half
Sure.
about your 2D problem?
Yeah.
Suppose we ask where the infinity comes from there. One way of thinking of it is that it comes from the volume of SL2.
Oh, okay, yeah, you made this great comment. I could never make it precise, but please continue.
Yeah, if you look at Stanford and Whittle, that's where it comes from, right? Because you would actually get volume of SL2R times continuum, but then they mod out by this volume. So I was wondering whether, since SL2R somehow is low energy, from the SYK point of view, whether this is correct only up to some cutoff. And then that cutoff in the SYK context will give you the e to the power. If this is true, I feel it's something, if there's something one can work out, sounds really interesting. That's the e to the power n.
Yes, this one can money.
Does this?
I think it might be. I have checked with you.
It does this size.
Because BSSY is exactly like it's not a double scaling. Okay, that one
I
is
understand.
triple scaling limit to get to data. But then it's looking out maybe.
Awesome. And I would like just to see physically that the RG flow that takes you from SYK to this gives you this SL2R with a cutoff. And if that cutoff more or less reproduces black hole entropy, that would be fantastic. That would be very physical.
This is, I think, should be.
Should be doable, right? Especially given you guys.
No, I tried and tried. I couldn't make it precise. Maybe it's not. I'm sure it's not. Yeah, but maybe
You're trying to the density of states is what I'm after. That here is quite weird.
if you include the boundary graph.
Oh, yeah, no, that's,
You will
I
have to
agree with that.
Literally red circle.
Absolutely, absolutely. This is why I'm saying that.
It's really from velocity represent it's very much right.
So it's very likely.
Primary versus descended from. So again,
Okay.
you will descended from the full non-zero mode calculation. Even the zero mode calculation as convention is already right.
But we know what the answer is going to be. Because that's just quantizing the boundary graph and it produces representative. So I feel you can break it up into two parts. The part that is basically all non-trivial solutions somehow, and the part that is these boundary graphs. It should not talk to each other. I feel that just put various cutoffs on this solution. Quantize those. They give you a boundary graph. Of course, big gap between saying these words and doing it, but feels like it's going to be.
Yeah, I would agree that if you look at the solution which includes the boundary graviton, which is all Virasovs, then I expect, that's what I'm saying, that then I expect actually that you can make more progress in the calculation of the density of states. The density of states is a property of the Hamiltonian, the Hilbert space, not of Hamiltonian. Okay. That's it. All right. Yeah. All right, so all this can be worked out. Now you come back to, so this is the solution that I presented this. Solving the Einstein equations, certain gauge, worked out what the lapse shift of this solution of the equation is, and this N and T are the time dependent coordinates. The time dependent solution. All right, so this is what we. Now this solution turns out to be diffeomorphic to a region of the fully extended BDC black hole. Now, there are a huge set of coordinate transformations. I'll tell you what I'm going to show you, but let me just tell it to you. So we have this solution in a certain gauge. The great thing about this gauge is ultimately I want to solve the matter field problem on it. I want to understand how the matter goes through the horizon. So this is the reason I chose the maximal slicing gauge. And from this gauge, now we will go to what are called aerial coordinates, in which the metric is always of the form r square d phi square. In the left and the right region, we'll find that the solution we get has singularities. So we patch it up. You can do that. It's all quite complicated stuff. Right? and simple but complicated. And you get a very smooth solution in terms of what we call now the wormhole coordinates. Okay. Then these wormhole coordinates form this chart, global chart. And that global chart is related to the classical chart by invertible diffeomorphisms. So this is the point in how to work from one chart to another, because you cannot solve things explicitly. You have to do all of these things. So let me just, this is what I will come to. I will basically try to understand the VPZ black hole, the classical diagram in terms of the maximal slicing. Okay, so maybe I should just go tense transparency slides down and just show you the answer. So these are the areal. So these are the areal points. So theta positive, R is given by this. So this is there is a solution to theta. And for the theta less than 0 on the left boundary, this is the chart, and you just plug it all in, and we get this type of answer. Similar formulas hold for the theta less than 0. Yeah. So theta goes from minus pi upon 2 to plus pi upon 2. This is from 0 to pi upon 2 and 0 to minus pi upon 2. There is singularity at the
Sorry, one last question, Sven. Sorry, so sorry.
on this slide? Or
No, yeah, yes, sorry. So sorry. It was that you have the density of states of a particle in infinite volume. Is this right?
Yes.
Okay, so and that infinite volume was because some coordinate was non-compact. What was that non-compact coordinate?
Here it was Q.
Q. And
Q
was what again?
M.
M.
So
Thank
M was classically not 0, but quantum mechanically it was. Thank you. So I was searching for compactness to get a good answer. But
P was your other conjugate variable, your Q and P. Right?
Yeah.
P was also
non-compact. Yeah.
okay.
Okay, sure.
Yeah, but you would still get a discrete, like in a particle and a circle. As long as one is compact, you get it discrete.
Absolutely.
So I was.
It's not. Actually.
It's
That's
not,
the
yeah,
problem.
but maybe not, but somehow it should become, right? That's the idea.
Even if you do that, like, it's not going to give you the exponential means, the non-perturbative.
Well, it depends on what the size is. If the size.
In fluid gravity terms, you're trying to quantize the fluid and see the atoms. Like that fluid modes, just quantizing the fluid modes are not going to show you the atoms.
I agree. I'm just asking, what is, if you put the final answer into this effective language, what form must it take? I think it should quantize, it should compactify something. But sorry, I agree.
Yes, then. Okay. Okay, so this is the type of algebra you get, and the important thing is that it's N, where the lapse singularity. And so you are a solution of the equation, and so the divergence that happens at the center of the wormhole, which I just mentioned intuitively. So you've got to match those coordinate systems, and the matching is done by introducing a new coordinate system, which is given by x function r and t bar. And to do all of that, then you get solution in terms of what we call wormhole coordinates. Now the key point is that the lapse shift of all metric components in this coordinate system are regular. This is the point of how we do that. And there is another coordinate system we know in which it is regular, and that is the classical coordinate system. So that means there must exist a differentiable map between classical and this. So we use this all the time. All right. So let me just go forward. So now eventually we come to the VPZ black hole. So this is how canonically VPZ discovered it in the region of to classical. There is a diffeomorphism to go from the radial coordinates to this. It's also given by this type of very non-trivial thing. So all of this stuff actually It's, I just want to say that we understand what we have done, even though it is very complicated. All expressions in these slides are all finite. And yeah, there are no divergences, and this is the point there. Okay. So,
Sorry, just ask you one question. I mean, Harlow and Jefferies also quantized this system.
no, this is, they did the gating.
Oh, they did GTM societies.
I had a related question.
Sure.
So, that was a data copy, but in their context, they use this length.
Yes, normalize it.
Not.
Important.
Yeah.
Yes,
The nice
that
thing-
goes from ICTS.
The nice thing about that coordinate was that the Hermitian Hamiltonian became very simple. There was no operator. So would that work? I don't know.
Yeah, I mean,
the volume-
that's the right question. I was wondering, is that variable worked so well?
Yeah. You might wonder that it's the
Yeah,
natural variability.
yeah.
And it's not really.
And so maybe a related question, that this phase space you can think of as being generated by just doing time translations on one side. Could you also do rotations just on one side? And get a double phase space, a phase space that's.
They're rotating.
But just even if you start with the non-rotating, you look at the tangent space around. It feels like there should be one more degree.
Yes, so I have plotted that out by my boundary conditions.
Yeah. Right, I agree. But I'm saying just if we wanted to do this Witten kind of thing, or whatever,
Yeah.
long you thing, you'd expect roughly one more degree of freedom for the set of primaries.
Yes.
Right?
Yeah, right. But it so turns out that that additional degree of freedom is Witten type. Witten basically it's the mass time relay certainty. Mass and time difference is basically canonical conjugate. I have questions about all that. But,
So that would basically make it holomorphic transactive because theta plus t will be 1, theta minus t.
yes.
So you'll just get a doubling of that.
Right,
Fusion story.
right.
Fine.
With M and J.
Yeah.
Right. Okay. All right. So you can do all this and then ultimately you arrive at the final. This will be the final. This slide is important because what it says in the following. It says that if you take the crustal plane, it is divided into 3 parts. I'll tell you what those 3 parts are. So this R naught essentially contains these boundaries also. And R1 and R minus 1 close the singularity. And this is true for the maximal slicing gauge in A dimension. This feature of the maximal slicing gauge, there's some sort of a cosmic censorship appears in this.
Again, they don't include the single.
This gray one is the one region I will be working in. But there are 2 other regions in which also you can do maximal slicing. But in some sense, the slices branch near the singularities. Now, this technique is used in numerical relativity because they don't want in their numerical codes to encounter singularities. So we learn from Baumgart's book on numerical relativity that this is a very widely used gauge.
Maximal slicing.
Yeah, some version of it. But they don't actually fix gauge, they fix n and ni. I go forward, I fix my n, another n, etc. That's how they solve the Einstein equations. Not like the way we do by gauge fixing and solving for n. No. I give you n because it's arbitrary. But they do this type of calculations of excising the singularity, the singular part. Otherwise, how will you be able to do the numerics of coalescing black holes? Okay, I just wanted to make that point that we are just not so far from what people do really in physics. All right, so this
Did I understand right? That the solution that we found
right,
is if you're not fixing is great.
great. I'll tell you why. So that's the name. Okay, this is how the slices look. The important thing is that all these slices go through the horizon, and the lapse never vanishes anywhere. So if you look at the standard slices people work with, they all go through the bifurcate horizon and there is zero there. That is the problem, as you know. So we found a game in which all the slices are such that the laps and shift are very well defined everywhere, going through the horizon. This was the reason why we might see classifications.
As you went through in the usual way, then lapse or something vanishes.
Yes, there is zero. What people say, oh, let me just lift it off a little bit using general coordinate invariance. I invite them to do it. I mean, you know, Stein was doing some talk like that. I speak. Okay.
One go to your husband, this is not good. You do it for me.
I don't want to do it. I'll tell you what the problem I want to solve. The simpler problem, not singularity, then next year. So, but this figure is important. This is the Penrose diagram that is the cluster diagram. And this is how there are these limiting slices, which I will mention what they are. These in red, these are the limiting slices. And this region that we are interested in contains the two boundaries. That's the important thing. That all the information of the conformal field theory is here. Okay, at least in this approximation. All right. So now,
Sorry, just
Yeah.
the boundaries of those two slices go up to infinity in boundary time.
yes. So the important thing in the way we have done it is that the time of the slice is the boundary.
Is that right? Okay.
Yes. It can, in general, it can differ by this c times t left plus a constant, or by c twiddle times c right plus another constant. But we fix those constants. My choice to have these symmetrical slices in the Hamiltonian evolution. Okay.
What is that? I mean, are we saying that the singularity region is sub A dot R?
No. There is another maximal slicing here.
Oh, there's an-
Yeah.
There's another solution.
Absolutely. Absolutely.
But how do they end on the boundaries?
This is what it is. Interesting.
But what if it's geometry of the solution? What if the geometry of the spatial slicing that entire region?
This region here. What is the geometry? I know the answer. What is it? I can solve this problem.
But just okay, forget geometry, topology.
Topology.
The way here it was cylinder,
Yeah,
you had
yeah.
one boundary here, one boundary here. It looks like there's no boundary there to end on.
No boundary closure.
So what does it end on? Singular points?
Yeah,
Sphere with this point?
Maybe. I didn't investigate that. So I was not interested.
You can't get arbitrarily close to the singularity.
No. I'm just far away from it. Like, see, I'll tell you the reason why this is happening. And this is happening because of this fundamental point. The lapse actually goes to zero at those limiting slices. So it carves out a certain region for you to work in. And this parameter eta is just related to the mass, just square root of the mass. Right. Or RE, or whatever you like. So are you with me? This is the point actually. This, all of this algebra was to convince you that you take this black hole and put it in the maximal slicing gauge. Incidentally, the Schwarzschild black hole was put in this gauge maybe 40 years ago by Wheat and Estabrook and many other people. I mean, there's a lot of literature in this subject. So it's not that we are first people to do it.
What physical significance should I assign to this maximal slice, limiting maximal slice? Is that a gate? That
Clearly, it's a wouldn't say artifact, it's an artifact of the fact that you work with these coordinates. That excise this well. But it has other good features. In the sense that there's a huge region over here you can go to. I can travel on these slices.
So suppose I was very naive and I said, I'm going to use classical coordinates, which are well defined. And now I choose classical time, which also marches up. Isn't it? I mean,
Classical time does not match with the boundary time. There's an exponential.
classical time doesn't match, but okay, it's some
No, I
way
mean,
of slicing.
Point is that there is a very nice diffeomorphism between our coordinates and the classical. Certainly, I'm going to use that all the time. But it doesn't have a very simple Hamiltonian picture actually. Because here the time of the slice goes and meets the boundary and the dynamics there and here is reflected. And what I'll do basically is solve the wave equation in such a way that the solutions are entirely written in terms of the operators on the boundary, which this gauge enables me to do, and write down the Hamiltonian in terms of gauge invariant optics, which will take you through the horizon. So, there is a lot of this algebraic quantum field theory work by Hong Liu and collaborators, who talks about some Kohn operator because of type 2 something algebras. There exists this operator will enable you to go to the horizon. And our work started by trying to find a concrete Hamiltonian.
You're going through the horizon using equations of motion, right?
Yes.
What? Yeah.
Finite.
What?
In a finite way. In a finite way. Usually it is not possible easy to do that.
I am.
Yeah. Okay. So that's any question?
No.
Okay, good. All right. So I was just saying that this region is basically defined by this object. So I will take time to be of the order of 1 upon which is the order of the inverse of the horizon. So I mean, my point is that I don't want to discuss the evolution of my system for all times. Firstly, there are two issues. We all know that if there is something called the scrambling time in this theory. Once you go beyond the scrambling time, using a very particular saddle point makes no sense because large n factorization breaks down. So we just stay far from there. And we are staying even further from the scrambling point because our scrambling time is beta upon 2 pi log n. Our n is very, very large. So our time is of the order of beta. That's the scale problem. And I think that's a physically correct thing to do. We will see why that is interesting, important. Okay, so shall I proceed now? All right, so all these different coordinate systems, which I will not go through because we already discussed them. And I come to the second part of my talk, which is really the problem we wanted to solve. And then we got into all this. You get attracted by doing good math. And then you spend your time arriving at pre-particle devices.
Just one question. Sure. Did you write down the wave function? Whether from you can write that. You see that.
Okay. So now what is the strategy here? Let me tell you the strategy. The strategy is firstly to solve the Klein-Gordon equation in the entire classical plane. So you may think that this is of course a solved problem. Yes, of course, there's a very famous paper in the 60s by Undu, which actually attempts this problem of how to solve the Klein-Gordon equation, especially because there are singularities at the horizon. Now, there are these oscillatory things, u to the power of I omega. If you have a wave of frequency omega, you get u to the power of I omega. You take a e to the I omega log u. Take a derivative, the Hamiltonian is not finite CP. So what we did is, just tell you what we did. We regularized this, we solved this problem first. We solved this problem by regulating the solution in a certain way.
Sorry, so just to say, even there, if you're interested in something falling in and you went to ingoing Eddington-Finkelstein, let's say.
I am interested in not that, I'm interested in.
No,
Going
I
to the
understand, but
horizon.
I'm just saying first, in terms of
Yeah.
solving equations,
Yes.
there are nice gauges where, you know. you
No,
can
I'm not, I'm saying it's not a gauge issue here. This is an issue of the fact that this is the famous blue shift problem at the horizon. This problem is not, it's there. You can't get away from it.
Okay, but in a sense, the guy falling in doesn't see anything funny. So if you choose a nice coordinate system, like ingoing Eddington-Finkelstein,
Pascal is that.
or you can do, no, you may say the other coordinate in Pascal.
Yeah. I appreciate what you're saying actually, but what I'm telling you, that you take that solution and try to compute the Hamilton.
Your boundary Hamiltonian. I mean,
No, I'm now in the bulk Hamiltonian. Bulk Hamiltonian is gradient field square terms.
Yeah.
And in fact, Unruh is pointing this problem out in his paper. And his solution is that re-expand into the I omega log u, re-expand as a new Fourier series. What we did is we did not use Fourier series, but we used a more discrete basis, the harmonic oscillator basis, in frequency space.
But I mean, ingoing would have been completely fine.
But that's not my
gradients
problem.
together. No, I agree with you. Then convert it.
That is not, no, you cannot convert. You
No,
tell
why-
me,
why not?
you tell me how to solve this problem. How to,
Okay, I would go, I don't know, I go from ingoing Eddington-Finkelstein to Kruskal to your coordinate system or something.
but what are you interested in? What is my?
I thought you were interested in your.
No, I'll tell you what I'm interested in. I'm interested in solving the Klein-Gordon equations with certain boundary conditions. Okay. Now I want a solution which is differentiable and continuous everywhere. You produce for me that, I'll be happy. Now I am giving you one recipe of how to do it. That's all I'm saying. It's not a big deal.
In your gauge, Spenta, you can just produce it, right? I mean, do you ever get singularities at the horizon?
No.
Exactly. Okay.
But we cannot solve the equation in our gauge. This
You
is
can't. Oh,
because it's mathematically very difficult. So we go to this way and
but conceptually,
you're absolutely right. No, that is said over there.
There
Right here.
are other gauges also where it's clearly
Sorry?
true. I mean, there are other gauges where it's also clearly true. We know how to follow things going through.
No, I'm not
In
denying what
gauge.
you're saying, but,
Okay.
but I am interested in a certain different problem.
Sure.
I mean, as Shiraz is saying, it's written here. You take this equation in our the maximal slicing gauge in the things I gave you, and you solve this equation. Numerically, you can do it because it's a hyperbolic equation. I mean, people who know numerics tell me that you can actually solve this equation, period. And you're completely correct because the coefficients are all finite. But I don't know how to do it. So what we do is we solve it in region 1, then region 2, then match the solutions in forward and past and produce a certain solution in the Kruskal coordinate system.
we'll say one thing, Spenta.
Yeah.
For a conformally coupled scalar, the problem very much simplifies. At some point, I've solved this equation very simply, but only for conformally coupled scalars. So the mass fields, you can just analytically solve.
I see. For what?
In 2 plus 1. Take a conformally coupled scalar. Then your BTZ metric is complicated, but by doing an appropriate Weil transformation, you can make it much simpler. Because it's conformally coupled, your solutions map.
So you can solve the full Klein-Gordon equation.
Shantani solved it long ago,
No,
but only just classically.
Classically, I'm also doing classically.
Yeah.
No, my point is that everybody in the world has solved these equations, but they
but this was
didn't realize that there were singularities there. That is the problem I'm trying to.
I'm saying in this case that you just take away. There's no singular for the maximal for the conformally coupled. It just breaks down for everything else. You've done much more.
I didn't know this. Fine.
Can we take this point of view that this BTZ blackula there is a quotient of ADS3? Then can we not solve this in ADS3 where we know how we should apply?
Solve what? Wait a minute. Correlation functions are exactly solved that way. But I am not solving that.
No, I think the solution, the explicit solution in ADS 3, write down, then make sure that the boundary conditions are such
It's possible
that
what you're saying, because the correlation functions are calculated by this Japanese group that way. That's known. What you're saying is right, actually. So in 2+1, there is this facility. But you see, I'm interested in a very specific problem. Can I construct a gauge invariant unitary evolution through the horizon, which is smooth and well defined? That is my problem. And I'm giving you one recipe of how to do it.
So for that, you clearly need your gauge.
Yeah. That I think is a meaningful question because
You clearly need your gauge.
okay, fine. So now let me, so this is all classical mathematical physics, which I don't want to go into. In 2+1, this are written in terms of hypergeometric functions. In higher dimensions, they are more complicated, but there are always complete sets in the Klein-Gordon norm to do this problem. All right, so let's go ahead. Now, I think this slide is very important because it fixes this problem of gauge invariance, which a lot of people are worried about. So suppose you have one-sided problem, one-sided line. So if you solve it in this, let's say the right region, this is the boundary. Then if you solve the equation here, you can have a boundary condition which expresses the asymptotic value on this slice in terms of the gauge invariant operators. Boundary operators are all gauge definition. We solve the problem on the other side of the horizon. This is the problem Surat and Kyriakos tried to do 10 years ago. To all this discussion about gauge invariance and Stomita-Takasaki theory. So, however, if you have two-sided, if you're working with equilibrium black hole, which can be put in two sides, then this problem is solved much more easily because you have two sides, two conformal field theories, and I can put my boundary condition here and here and reconstruct the entire finite solution in terms of these two. And so my scalar field in the bulk is gauge invariant. This is a problem a lot of people are discussing.
So give the two values in a sense,
Yeah.
asymptotically.
Yeah, exactly.
And then you solve, right?
Exactly.
It's sort of like HKLL for the double-sided black hole.
Right. It is sort of like that, but it is not HKLL.
Okay.
Because HKLL have some very rigorous steps as you go across the ones. Say that.
The T and T are forward in both the CFTs.
Yes, in this exactly. I fixed C and C equal to 1. That's it.
Yeah, I never believed HKLL once you go past the horizon.
Okay, so that's where the problem is. Okay. There is a problem there. Yeah, I know it. Bringing on to it. Okay, shall I go ahead? So
The solution is a kind of solution which is like going on understanding the
yeah, I mean, so no, I mean, no, it's go.
It's even more than.
Most general. Right?
Most general solution. is
Locally, you could set up the future horizon, and I think locally Spenta will have both this as well as.
both. Absolutely. Yeah. It's just a static solution in this box, the ABS box. Okay, so I was quite excited that this gauge invariance problem, which I find so many people discuss, is very simply solved because I'm doing two-sided extended line. Because I have this other boundary to work with. Otherwise, it's a difficult problem. So what people do usually is they take the scalar field in the behind the horizon, then transport it in some way by some Wilson line or something to this boundary, and then compare it, and it becomes complicated. But here it's very elementary. I just wanted to say that. This is a key point.
Usually, one could have just specified phi and pi
Yeah.
on some G zero slice, and then they wanted to select.
Yeah,
And here you're specifying, oh, I don't till and.
exactly, absolutely. Okay, so now this is all this new stuff, how to now go to the Hartle-Hawking modes. So these are oscillators of two conformal field theories. You've got to make a Bogolinkov transformation so that you get the right operators and the Hartle-Hopkin thing. You go on. So this is something. It's not trivial, but it's sort of well known. This is a highly non-trivial stuff. Well known. So here it is. So now we are ultimately arrive at the Hartle-Hopkin wave function. So the operator that we work with are these. These are the linear combinations of A and B. These are the famous factors, the Bogolinkov coefficients. The square root of sigma, etc. All this can be worked out. It's all very well known. And we define a vacuum in terms of these annihilation operators. And that is the Hartle-Hopkin vacuum. You can see that.
It's shown. I lost something here. The omegas refer to the asymptotic boundary
frequencies. So that's the point, Sanjay. It's a very important point that the omegas are the continuous frequencies because we are working at n equal to infinity. You see, if there is one gap in this entire thing, is that how to do finite end. Okay, so good point. All right, so this is the Bogolinkov stuff, and you have to when the Hartle-Hopkin vacuum arrives natural in this way. Okay, so the Hartle-Hopkin state is a highly entangled state in the inverse space. Theories, etc. Now we come to this finiteness question, which I discussed. And so if you look at the solution of the line-Gordon problem near the horizon, there's all these factors, these oscillations going on. And if these oscillations I wanted to cure, and Unruh has noticed this, I mean, he has suggested a cure. This cure was to expand this divergence object in terms of another Fourier series. But what we did, we adopted a more discrete series, discrete set of bases. That's a harmonic oscillator wave functions. And this eta we put on physical grounds. It can be 3 eta also, 4 eta, doesn't matter. And then you can see that the behavior, all of these things is perfectly all right. You smoothen out everything because of the exponential in the frequency space.
So Spenta, you can expand your, when you try to solve this wave equation, you can expand an e to the power I n theta.
Yes.
But there's nothing else, right? It becomes a two-dimensional partial differential. Because there's no other.
Absolutely. Separation of variables.
But there's no, but you cannot make it ordinary differential.
So, all right. So this is the important point. So this is the expansion now we are working with Pascal of these functions which are regulated, and these are the modes. And the important thing is that this thing which I will say, let me say right away, that because the classical map and the harmonic coordinates map is 1-to-1 diffeomorphic, I can claim that I have also solved the problem with the original coordinates. Yes, harmonic coordinates. The maximal slicing. I can say that precisely because we have shown all these things will go into each other. The ideal thing, as Shiraz was saying, is better solve in terms of t bar x and phi, but it's very difficult.
It's
very non-trivial. Numerically, Anurag said, give me, I can do it. Numerically, no big deal for these people. Okay, so this is the basis we work with. And these are the discrete modes. They're labeled by N, by Q, which is the angular momentum number. And we claim that we have a solution for the expansion of this scalar in terms of these coordinates by this equation.
Please remind me what Q was, please.
Q was the angular momentum. E to the I phi Q.
And N was?
N is the mode expansion.
That's like a radial kind of.
No. Yeah. So, no. So there's a frequency, no? The frequency.
IN.
Yeah, and then we bend the frequencies using the Hermite function.
And the frequencies all mix in evolution, right?
Oh yeah, that sure. Yeah, it doesn't separate out.
Because there's no time like it.
Absolutely, that's the problem.
Yeah.
Okay. So, all right, so this is the slide I wanted to get to. And this is the Hamiltonian that we have. Now, all the things we have done, we just put in and we arrive at this Hamiltonian and tell you what these matrices are. Finally, we work with the normal order Hamiltonian. Okay, so these are the matrix of these things that enter the Hamiltonian A star and B star. So we get a symmetric.
And these are how you're expanding the phi's.
Yes, that's right. So we had the modes, the Hartle-Hawking modes in terms of frequency. Now I take those modes and I pin them in a certain way. Problem?
No.
Looking at your face.
I'm
All right. Okay.
And then you get your
Yes.
these modes.
Okay, fine. Everything is fine, but how do you know this is all good? How do you know this is a good Hamiltonian? That's because it's all very complicated. So now I will argue as a physicist, actually, it's not mathematician, why this is well defined, there's a well defined norm and all that. This, no, if you read Witten's papers, he's always doing all these things, you know. Norm of Hamiltonian on the state should be finite, perfectly correct point. Now let us see whether our fellow is okay. So we can compute these. So it turns out to be the trace of B star B.
This each hat is the Hamiltonian of your scalar seed.
Yes.
Oh,
Right.
it's not the boundary.
No. Boundary hai nahi, put there. I mean, it is written in terms of boundary modes. Now, I don't know what you're saying, huh?
So it is, so there are two notions of Hamiltonian.
No.
There is the Wadia Hamiltonian.
Yeah.
And so there is this integral of P00 to the bulk.
Exactly. But what I'm doing is, this is not the alien. Alien was to pure
So this is the bulk.
It's the bulk. But I have expressed the Hamiltonian entirely in terms of boundary operations. So the point is, I would say it's as well a operator of the two boundaries.
Yes. But just to say it's the bulk.
It's like some sort of a welfare type of problem. Sorry.
No, I just want
Yeah,
to
yeah.
say it's the bulk.
Yeah, it is about. But written in terms of those values.
Just.
In the Hartle-Hawking state, I can define as usual annihilated by the Kruskal modes. Like we do.
Absolutely. Or by path integral, several ways of doing.
But you probably did it in.
It just come out naturally.
I mean, because you can't very explicitly solve for the modes in your basis.
Yes. So we could do that using this. We go to from the VDZ coordinates, you go to Kruskal,
Then you bin the Kruskal.
build the Kruskal.
But anyway, you know what the vacuum is in Kruskal, so you do it.
Absolutely.
Okay.
That can be shown.
Yeah.
That's easy because it's all linear continuity.
So I should ask pointed out there is seemingly more time like killing vector. So what is thinking?
Yeah. So that's why this Hamiltonian is so complicated. It's time dependent. No. All of these coefficients.
It's the bulk in it.
It's the bulk Hamiltonians. These are all on these slices. And that is why it is so difficult. This is what they are.
The local.
Yeah. So, okay, now this is important. There's a sum over n and n prime and q and p prime. And I can argue physically why this trace is finite. For simple reasons, actually. So there is so omega comes from, from the, you have the Hermite function, Hn of omega, right? So you ask yourself, if you take harmonic oscillator and you're at a certain level, how much you will go? That's what it is. The innate Hermite function is proportional to spatial spread of the function is proportional to this ordinary. I looked it up. I forgot it. And this too. And the range of Q is bounded for an even nicer reason. all of us who have studied black hole problem, absorption and all that, we know, just think it's an object, some finite size, and you're scattering some waves. So if you want to get there classically, you got your impact parameter has to be less than the radius of the horizon. That puts a nice bound on the angular momentum. And therefore, I believe the bound is just given by root of f.
Does it grow with time?
Huh?
Does this thing grow with time?
Does this thing grow with time?
And how does it behave as a bound? Asking whether this wave function is very. That's region sense.
Yeah. So there's a Lax function there, which dies in time. I showed you that the Lax actually goes to zero exponentially. No, now I remember. It's perfectly fine. Doesn't go off and do deeper. Okay. So I am near my boundaries of time. So let me just so we can now talk of evolution. After that talk is done, I have hopefully convinced you that I have a Hamiltonian that will give. So I can construct some states actually from my oscillators and evolve them by this. That is the idea of smooth sort of evolution in the horizon. And yes, your answer your question.
Can I ask a physical sort of, which you may answer, which is intuitively, let's take a wave packet which is entirely on the left to begin with. Now you might think you'll be sort of imaging it on the left to begin with, and then as it goes, there's something.
No.
What happens as
No, so exactly. I mean, you're sure. But the moment you start moving, they all mix up.
They'll mix up, but is there a signature of crossing into the region where you see which the upper Milne wedge, so to say, in your boundary description? Can you see the horizons in the boundary description? Just to ask, because in a sense, boundary time ends when you cross the horizon, right? I mean,
That time I'm not using.
I know you're not using it, but I'm just saying,
Yeah. So
the boundary observer would see the wave packet cross.
So now there is a problem with your question. I'll tell you, and this I'm struggling with a little bit how to understand it. There is no the left and right fellows, Joe and Jill, whatever, whoever they are. Those oscillators are all mixed up in this Hamiltonian. So I would like to understand the thought experiment you are suggesting. So I know that if I construct a wave packet in terms of these oscillators, then I will recast it to my oscillators and see how it goes. There is one issue here. Let me point out this problem. The eyes are closed.
I'm thinking, yeah, please.
Is the following, that you may ask that this Hamiltonian I have taken in this basis. So if I go back and back and back and rewrite it in terms of the oscillators of the boundary theory, the A omegas and A dual omegas, you'll find that these coefficients are all divergent. This question people ask me, but this is the answer. If you write this Hamiltonian in terms of those modes, then these coefficients A, B, corresponding ones are all divergent.
Perhaps a nice wave packet in terms of the modes there, left or right, might still translate to something which is convergent. I mean, because you're cutting off the very high frequencies.
You see, but Sandeep, the point is, what I have realized is that it is very easy to say and ask, this can be done, that can be done. I find it very difficult actually to do these mathematically, actually. I mean,
we could try to translate the question into Pascal-like of Eddington-Finkel-like coordinates and try to cast it in your.
I understand what you're asking. The question is whose state am I considering? So if I look at these oscillators, they belong to both the sides.
Intuitively,
So,
what
so
you
the
might
issue,
expect is,
so the issue is another thing which I don't know how to do, is how to trace out. How to trace out, how to trace out the left moving degrees of freedom in this formalism. I don't know how to do it.
intuitively, you might expect the following, that the image in terms of you have a wave packet going in and you have an expectation value of some operator. Now, if you put a cutoff in frequency, a boundary time frequency, then the expectation value of O will go to zero. Because for it to have non-trivial value as you're crossing the horizon, you need to have very high frequency availability. So, if you bin and cut something off and then you image, the image should go to zero. I mean, something like this is the horizon signature,
Yeah.
Okay, anyway, let's talk later. But
the point is usual horizon signatures are ultraviolet divergences, singularities in the metric. Now I'm giving you a formalism in which I removed all of that.
Yeah, but the physical meaning of the horizon is if a starship falls in and they only have some finite frequencies, as seen in the infalling frame, no signal after a point reaches up, right?
No, I agree with that.
So
no, I understand. I think it should be possible to extract this out of this formalism. Yeah, so let me just conclude. This is so you can go to a slightly better basis actually, which some nice things you can do. Okay. And then you can compute correlation functions, and you introduce standard answers. Just one comment. The important comment is that you don't see any thermal behavior if you work in these coordinates. Thermal behavior you are able to see only when you sort of make a coordinate transformation which is singular on the horizon. That's what gives you the thermodynamics. This is a very beautiful point.
What kind of thermal behavior would you like to see, Spenta?
I mean, the standard, the fact that there's a temperature associated with this black hole. After all, we are working with pure states, not to begin with. So we are working with pure states. Now, if I'm able to sort of trace out the standard thermophile double idea, then I will have a thermodynamic description of the right boundary or left boundary. Now, I'm not able to do that, the tracing out, but somehow I feel that general relativity is helping me do it. I take this system and I make this transformation to this region 1, which is bounded by the horizon and the boundary. That transformation is singular. It's a large transformation. And because of this, the thermal behavior. There must be something here actually. GR knows.
In the bulk, that tracing out will be singular, right? Because it's a field theory, you will trace out.
I'm talking about tracing out the boundary operators, because they're boundary operators.
Yeah, I'm just thinking in the bulk it's singular, but maybe after you bin, perhaps you make it, that binning is important somehow. I mean, trying to make it fun.
Yeah, certainly.
Also, the singularities will be sort of the kind that are cancelled by renormalization of Newton's transcript. So if you do that, maybe that removes. Suskenuglu. The kind of thing Sandeep.
Suskenuglu. I mean, between the two formulas for entropy.
Yes, meaning that if you compute entanglement entropy. Sorry, one. Okay, after you finish.
Yeah, let me just the summary goes on. I think I have to. Thank you. Forgot to say.
So one signal of thermal behavior is dissipation.
Yes.
So I was wondering whether if you take an arbitrary initial slice and then you follow the solution to late times, you look outside one of the horizons, will the solution now be expandable in the usual quasi-normal modes? I'm wondering whether all solutions of this initial value problem, if you go long enough, have an asymptotic expansion in terms of quasi-normal modes of the ingoing quasi-normal modes here and the outgoing quasi-normal modes.
I don't think so.
You don't think so?
This my gut feeling is that moment you work with, how shall I put it? Yeah,
The full thing.
Yeah, the full thing, which is
Then quasi-normal modes have no particular sense.
no. That's right.
But I was thinking, Spenta, that the modes that go. So basically, what you're hearing is that there are modes going like this and like this. The difference between quasi-normal modes is you also have the modes going like this.
Yes.
But I thought those decay in time. This usual decay on the horizon, these decay in time. So at late times, you'll only see this.
Yes.
Is that I was wondering that?
No, I think my point is you will never see dissipation if you have a unitary evolution.
Yeah, but you should trace out. That's very important.
If I couldn't.
No, I agree. I'm just saying.
But that just means look on one side, right?
Sorry.
Next, look at the expansion on one side.
Yeah, exactly. Just look at the solution outside the horizons. That could dissipate, right? The stuff inside the horizon.
No, that's what I was asking. How do you see it in a precise way outside?
Yeah, no.
Just the bulk situation.
Yeah,
Bulk
the
situation.
point is if you have a solution in all three regions,
Yeah. Then nothing happens. It's Hamiltonian.
that's what I'm saying.
Yeah, but I was wondering if you just stay outside the horizon.
Then I would agree with you if you are able to do
I
it
have a
that way.
feeling that there you will get an asymptotic expansion in terms of ingoing quality.
No, I agree.
And that will be the signature from the boundary that is insufficient.
No, I agree. I mean, in a sense, you can derive the existence of temperature also very much more easily.
Yeah.
That.
Yeah.
I mean, by looking at this KMS condition, which you can see here.
Could I rephrase your question? Something like, say, a norm outside the horizon ring for this scalar field?
Yeah, like that. Charge. Let's compute the charge. Take a charge scalar field. Compute the integral.
Yeah, that's clear. Yeah.
It's very clear. Yeah.
So this large transformation that you're doing to go to your nice coordinate system from your point of view, can I interpret it as basically losing track of an equilibrium time because you no more have thermality, KMS, equilibrium.
It's possible. So let me put this question again, which is really puzzling me. That in view of averaging out or tracing out degrees of freedom, we make a singular coordinate transformation and get thermality. That's what's happening actually.
So let me then maybe I thought you couldn't do the following calculation, but let me just ask you. Let's make a wave packet. And let me put it in Pascal code. Wave packet and follow it. After a while, the wave packet has disappeared in Pascal coordinates from one region. Because it's securely in the upper mid level. We track the expectation value of O of the field theory operator as you go along in Pascal slicing, but we'll convert to yours.
Yeah.
Is there a signature when the wave packet crosses them? This is the zero, but it seemed to be hard to answer.
I mean, what I can say is that the oscillators start. If you really follow the Hamiltonian from one step to another step, you will have to look at commutators of oscillators from one side and the other side.
So expectation value of O is very hard. Is it the one side?
Something should we expect just exponential decay? No particular time.
Okay, but
because
there should be some signal, right?
Just exponential decay. I think you see exponential decay beyond. But because it's all quasi-normal. Suppose you do the one-sided problem. You send from one side, then quasi-normal goes active.
Then I would say that's the quasi-normal. See, yeah, if you see the exponential decay, that's what then that's the quasi-normal. No.
Yeah.
Just in the 1 point function.
Could I say one thing though? Spenta is doing stuff, roughly speaking, stuff from here and stuff from. Okay. And maybe even stuff from the singularity. Maybe the more important thing is stuff from the singularity. He would have stuff going out of the singularity and stuff going out of the mode. Roughly. Right? So that's this mode and this mode.
Shiraz, he can set up the initial condition.
However he wants.
So let's set it up in a somewhat simpler way, nothing from the singularity.
If you do that, you just equals.
Then, so I thought you couldn't do that, but if you can do that,
I don't see.
If you can compute the expectation value, you should see some signal of crossing and presumably exponential decay.
But something that's as interesting, I feel, is suppose you don't set up that combination. Then even so at late times you should see quasi.
So which one you read? Something that we still.
Yeah, something from the singularity. Suppose you at some finite time you've got a mode going like this and like this. But even so, at late times that should be. So at very late times you see only quasi-normal. So roughly for the same reason.
Sorry, sure. Both sides you said. And then you see both sides the quasi-normal modes for each.
But suppose I'm on the right side and I'm looking at the future event horizon on the right side. And I'm more going along this horizon.
You'll see on that side.
Now this thing for a while you will not, right? Because it's got this, but it will decay away. So at late times, you see quasi-normal mode type behavior. I would imagine.
On the other side.
No.
Wait,
With the blackboard.
There's a calculation I can plug in.
I'll after the talk.
Two-point function if you complete. With 1 point here and 1 point here.
That's what you read.
Very good. Yeah, 1 point here, 1 point here. You do it. This calculation can be done. People have computed formulas for two-point function using this quotient of radius. And this is the behavior we find. C bar goes large. Goes this way.
It decays, yeah.
Yeah. Yeah, that's what happened. This is sort of something which Malvasena computed in his original paper. Now you do this. Look at this. Two-point function here and here.
Exactly.
Then it just goes to some.
Yeah. So it has to be somewhere.
Yeah.
It's all just behind the horizon.
Right. And then finally, this is the one I was referring to, where you see thermality. You don't see any thermality otherwise. There is no KMS condition. Okay.
I think just one last question, very elementary question.
You said last question, huh? Don't say that.
Since you have a harmonic oscillator, how are you interpreting the coherent states of that combination?
Too difficult at this time to answer. Not able to.
So this I understand. Okay, it's interesting. You have the 2 points here and so on. But what Shiraz had something else in mind.
Let the talk here.
Okay.
Any other
questions? Spenta again.